Okay, so this is another community type paper where a bunch of scientists get together and write a review on the topics of various interests, and this is a global overview of marine heat waves in a changing climate. So we know global warming is happening. We know we always talk about duration, intensity, frequency of extreme events like heat waves on land, and marine heat waves have become now quite popular in terms of the research topic as well as high profile papers, and some known impacts exist. For you, if you are a student, young scientist, then obviously you have to start thinking how reliably can we detect them and predict them, and even if we did, what can we do with them, and how do we monitor them? You know, if you predict a big heat wave is coming and going to hit the Great Barrier Reef, what can you do with this, right? Nonetheless, people make efforts. A nice observation system was put around the Great Barrier Reef, and they found some good results. People like Alistair Hobday from Tasmania, I think he's in Cyril, do great work of managing fisheries and so on down there, and also look at how things may get affected in the future and how to manage fisheries to deal with the coming changes and so on. So marine heat waves will be part of that. So this is led by Antoinetta Capotundi, as I said already. If I haven't said it, then it is Antoinetta Capotundi. So marine heat, it's a nice long paper, lots of very nice references. I'm going to keep it brief as usual. Marine heat waves have profoundly impacted marine ecosystems over large areas of the world oceans, calling for improved understanding of their dynamics and predictability. Here we critically review the recent substantial advances in this active area of research, including the exploration of the three-dimensional structure and evolution of these extremes, their drivers, their connection with other extremes in the ocean and over land, future projections, and assessment of their predictability and current prediction skills as well. To make progress on predicting and projecting marine heat waves and their impacts, a more complete mechanistic understanding of these extremes over the full ocean depth and at the relevant spatial and temporal scales is needed. So still underway, together with models that can realistically capture the leading mechanisms at those scales. We need to advance process understanding and then understand whether they can be predicted, what the predictability is. And remember, ocean has high heat capacity, it's several kilometers deep and slow variability. So what is the definition of a heat wave then? We'll see that that itself is not completely settled. Percentile type definitions have been taken from the atmosphere, where we don't worry so much about the 3D structure other than the processes of creating heat waves, local versus waves versus advections, ocean air masses coming in and so on. But we mostly worry about surface temperature percentiles that exceed thresholds and then cause problems for people, for crops, for ecosystems as well as livestock and so on and so forth, right? So sustained observing systems as well as measuring platforms that can be rapidly deployed are essential to achieve comprehensive event characterizations while also chronicling the evolving nature of these extremes and their impacts on our changing climate. Okay, their impacts in our changing climate, not on our changing climate. So it's a good story. Historical marine heat waves and their unprecedented summer of 2023. We've already discussed 2023 several times in the podcasts already, pointing to the fact that we didn't expect it. We still don't know why it got so warm, and you know, it'll continue. Global warming overlapped with a strong El Nino, and maybe the volcano that had gone off before that in 22 in the Pacific Ocean threw up a lot of water vapor, the air got cleaner, wildfires contributed to greenhouse gases, and so on and so forth. Nonetheless, that is now part of the story. Recent decades have witnessed the occurrence of MHWs, marine heat waves, that were particularly intense, long-lasting, and impactful. So we'll see a figure immediately. These most prominent MHWs generally occurred in different regions at different times. However, the boreal summer of 2023 recorded global monthly mean SSTs at record high since the beginning of the instrumental record. So we broke all records on land as well. If global warming, global mean temperature is very high, likely that ocean got involved, and El Nino of course throws out the ocean heat into the atmosphere during that event as well, right? So that is associated with warming in the tropical Pacific, but also often with the Atlantic and Indian Oceans in the tropics, and now this is talking about everywhere, right? So obviously many unusual things happened. Okay, there was a record large fraction of the ocean experiencing extreme conditions in summer of 2023, as illustrated by the widespread SST anomalies above the 90th percentile compared to the 1982 to 2011 baseline during July 2023, as we'll see. In particular, the average North Atlantic temperatures reached levels of warming that exceeded 4 standard deviations of the 1980 to 2011 period during parts of July and September 2023, with an average of 0.23 degrees C higher than in 2022. So of course you have to say that these happened. These of course are always looked at for impacts on climate, like hurricanes and their rapid intensification, etc. But in terms of marine heat waves, what did they do to the ecosystems, ecology, corals, fish, whatever, right? So what caused this unprecedented global extreme? The developing El Nino in 2023 can be expected to have caused an increase in radiative heating due to the influence of the El Nino SST pattern on the atmospheric static stability and low-level clouds. In addition, El Nino can alter the atmospheric circulation and cause the development of SST anomalies in different regions of the world, like the North Pacific and the tropical North Atlantic, although warming in the tropical North Atlantic usually occurs after the peak of an El Nino event rather than during its development phase. The pattern of Atlantic warming is consistent with the negative phase of the North Atlantic oscillation, which was indeed strongly negative from mid-April to mid-May and most of July 2023. So the paper discusses how natural modes of variability are superposing on global warming, of course, and multiple natural modes of variability like NAO and El Nino can interact, and marine heat waves often have natural modes of variability like El Nino, La Nina, PDO, etc. Interacting with them, and sometimes predictability comes from them. For example, the monsoon predictions often rely on El Nino. Similarly, El Nino produces specific teleconnections in other oceans which can be associated with heat waves as well, as we will see in a minute. So there are hypotheses built on based on these, but I won't go into these because we have already talked about how the Hanga High Pi volcanic eruption in 2022 and El Nino together added to it. There was reduced aerosols coming out of the 2022 21-22 COVID lockdowns and so on, but basically at this point we don't know the answer. But nonetheless, you can look at historical marine heat waves from Kuroshio Extension region, 2012 September, Gulf of Alaska, 2014 Northwest Atlantic, Mediterranean, Bay of Bengal, East China Sea. This is NA would be southwestern Indian Ocean. This is should be southeastern Indian Ocean. Okay, North Australia, West Australia, I guess. Tasmanian seas, of course the Nino 3 region, western South Atlantic and the Benguela region, and so on. Specifically for July 2023, you can see the same regions lit up, but large patterns of warming or warm anomalies here, where, as we said, some of these exceeded 4 standard deviations and so on, and of course strong signature of El Nino is there. How many of these are El Nino related teleconnections? Well, you have to see. So ECS-NA here is Northern Australia. It's way up here, but called Northern Australia, but anyway, so be it. So jumping ahead, influence of trends on marine heat wave definition. there is a nice discussion of what the heat waves should be defined as. So here is, let's look at this first. Defining a marine heat wave involves multiple choices, each leading to outcomes with distinct implications. These choices may be motivated by the need to understand the physical drivers or impacts of MHW, or they can be constrained by the characteristics of the available data like record length or temporal resolution. So there is a push to also have impact-based indices that can be predicted, so that just having a heat wave definition that is unrelated to impacts, and then predicting such a heat wave index and then saying look what impacts may be occurring can become complicated. So can we just include the impacts in the heat wave definition itself? For simplicity, MHWs are have typically been analyzed using local definitions. However, since MHWs have a three-dimensional structure that evolves over time, other approaches are emerging to facilitate the tracking of extended surface or subsurface events over time. So we'll look at the processes in a minute of how the 3D structure of the marine heat waves may evolve. Over the past decade, the majority of studies have adopted a common framework for defining MHWs. Following the widely used Hobday et al. Framework, Alistair Hobday that I mentioned, a marine heat wave occurs at a given location when daily sea surface temperature anomalies exceed the seasonally varying 90th percentile of climatology for 5 days or more, with dips below this threshold for 2 days or less ignored. So that goes to basically looking at duration, also intensity and frequency of the heat waves, right? So the 90th percentile climatology is typically based on a fixed reference period or baselines. Okay, so going back here, this is the SST anomaly for July 2022 with the trend included. If you removed the trend, then you would see the temperature anomaly that is independent of the background chronic changes that are happening. So you can look at that here over time, going from here 1980 or so to 2022, 4 I think. This paper just came out. SSTA with trend, so here are the percentiles and you will see how the exceedances happen. If you remove the trend, then you see that couple of them pop up here that were missing here, but they become much less here, which means obviously the trend is adding to the marine heat waves, which is expected. If you have chronic warming happening, then the baseline can determine how often you jump out of the percentiles that you defined based on the baseline, right? Observations for characterizing marine heat waves. Obviously, you need massive infrastructure to monitor them, but they talk about in the abstract quick deployment. So if there are hotspots like the Great Barrier Reef or the Gulf of Alaska where there is valuable fisheries, for example, can you quickly deploy something for intensive observations so that you can understand the processes of evolution, processes of heat wave formation, their predictability, and so on. So observations are the foundation for characterizing and understanding MHWs. For more than a century, a diversity of ways to measure ocean temperatures have been developed, from in situ stationary and moving platforms, both passive and active, to remotely sensed methods from satellites looking, but satellites only look at just the skin temperature, and here for heat waves you really need 3D structure or the heat content often. So they have a nice long list of things with some figures on how the Great Barrier Reef was observed and so on. I'll skip ahead to drivers of surface and subsurface marine heat waves. The processes driving MHWs affect their characteristics, including duration, intensity, and vertical structure, and are key for predicting their evolution. MHWs are driven by local heat fluxes associated with synoptic atmospheric conditions or ocean advective and mixing processes, and are sensitive to the ocean state, such as the mixed layer depth. Well, that's the whole kitchen sink in the sense atmosphere and the heat flux are involved, at least for the SST. Mixed layer depth is of course required for for SST, but ocean interior advection can be happening, waves can be coming by, El Nino can be adding, and so on and so forth. So they talk about these in detail that I have skipped. So these local drivers themselves may be modulated by large-scale modes of climate variability or anthropogenic warming and vary regionally and seasonally. In the extratropics, intense MHWs are commonly associated with persistent atmospheric highs, resulting in increased insolation and decreased wind speeds that reduce turbulent heat losses and vertical ocean mixing. So if you have typical heat domes in the atmosphere, then the winds die down, so latent heat loss is reduced and ocean begins to warm up, and the dome has no clouds, so you are beaming down solar radiation at full blast and giving enough energy for the ocean to warm up as well. So, and these can last for days to weeks and can really create marine heat waves. And the weaker winds also reduce the ocean mixing, which could bring cold waters and cool down the upper ocean and so on. Associated shallower mixed layers can further amplify the warming from surface heat fluxes. More broadly, heat budget analyses indicate that increased insolation and reduced evaporative cooling typically dominate the buildup of MHWs, while decay is commonly driven by increased turbulent heat losses. Okay. That's kind of a general typology. In boundary current regions, anomalous warm oceanic advection is often important. So it's like in the atmosphere, a air mass is coming, or a wave is coming, or local dome is forming, and so on. And here the same thing can happen. When the heat wave is decaying, you have increased turbulent heat fluxes because the winds are picking up, mixed layer is entraining cooler waters, and so on. In boundary current regions, anomalous warm oceanic advection often is important. Key examples include the 2011 Ningaloo Nino on the Western Australia and the long-lived 2015-16 Tasman Sea marine heat wave on the southeastern side. Advection-driven MHWs typically have a smaller surface area but last longer and may reach deeper than atmospheric-driven events. Atmospheric scale can be larger. Ocean advection happens in these narrow currents that can last for a longer time, but they are narrower. Okay. And they reach deeper. In the tropical Pacific, MHWs associated with El Nino Southern Oscillation are dynamically driven, with surface heat fluxes damping temperatures during both onset and decay phases, because their warmer temperatures can mean the ocean is taking up less heat. Typically, when ocean dynamics brings up cold waters, the atmosphere is trying to heat it, but if the ocean heats up by dynamic processes like El Nino, then the heating from the atmosphere decays or drops. In high energy regions like western boundary currents, oceanic mesoscale eddies and meanders, which often cross onto the shelf, can contribute to the onset intensity and longevity of MHWs at small temporal and spatial scales. Changes in atmosphere-ocean interactions, including positive cloud feedbacks, so reduction of low cloud cover leading to enhanced insolation, for example, and that is in response to the initial SST anomalies, and these can all contribute to the maintenance and intensification of those anomalies and increase their persistence, as documented for long-lasting events in the Northeast Pacific, the Gulf of Alaska region, which is where this business actually started, the so-called warm blob, which started appearing and lasting longer. Nick Bond started calling it the blob, and then people started seeing dead fish showing up and ecological impacts and so on and so forth. So obviously ocean has a nice 3D structure, and to the heat waves, their growth processes and so on. So in the shallow regions, in the bottom at the coastlines, extended eddies, extended coastal currents, and you are looking at the open ocean kind of structures where mixed layer dynamics is involved, waves are involved, and you have, of course, surface heat fluxes involved, and you have advection processes which can dome the thermocline and create trapping of heat by shallower mixed layers and so on and so forth. So here net ocean heat flux is into the ocean, winds have weakened, So that reduces latent heat loss as well as the mixing and shallows the mix layer, which means the heat flux can do even a more efficient job of warming the temperatures, and this typically happens in shallower waters. But when you have alongshore winds pushing into the coast, you can have downwelling, and you can have accumulation of warmer waters, and the thermocline is sitting there. You can see this is kind of a advection related to the convergence of Ekman flow into the coast. And you can have extended eddies. Of course, you have the front or the eddy edge on this side, and you have cross shelf migration that we talked about. This typically can happen in the western boundary current regions that we talked about before. Okay, so this is the extended eddy, and extended coastal current can also happen. So you have things like the Gulf Stream or East Australian current or the Lewin current and so on, which can then interact with the mix layer, which is here relatively shallow. So you have transports going, we are looking at the tail, so it's going into the page. So you have strengthened and warmer boundary current happening because of the extended coastal current. So these are kind of schematics, and you can look up the words here, but they are basically saying what I'm saying. Here again you have net heat flux and weak winds, so you can imagine a dome-like situation. And on this side you can have build-up of a heat wave and the decay of a heat wave. So here net heat flux begins to cook the ocean. Weaker winds also reduce heat loss and mixing. So you build up a shallower mix layer and a heat wave, but then winds begin to pick up. Relatively speaking, heat flux begins to increase, mix layer begins to deepen and entrain cold waters, and the decay can happen. And of course, ocean is full of Rossby waves, which typically propagate westward unless they are short Rossby waves at the coast or so, but this is just a relative direction, and they can induce, it can be a downwelling Rossby wave, so it can deepen the thermocline and converge warmer surface waters and create subsurface heat wave, marine heat wave, in the sense you have an anomalous blob of cold water that is not showing up at the surface here because you're just converging surface waters and creating warmer, deeper thermocline here. And this is a case of let's see how they describe it. I'm just jumping ahead, but nonetheless, G is when you have persistence of deep anomalies with no surface signature due to the mix layer shoaling. So mix layer is shoaling here. Heat flux is going into the ocean, and on this side heat flux is being lost. So you have kind of a subduction of warmer waters below the mix layer. So heat is actually entrained below the mix layer, so that even if you want to entrain with turbulent kinetic energy at the surface, you may end up entraining warmer waters. You can think of this as a kind of an inversion here. So it's a kind of a schematic situation, but it does happen. So these are the typologies from observations, obviously. And finally here, emergence of deep anomalies at the surface when the mix layer deepens. So you had subduction, so there is a memory which is not mixed away, and then that can get entrained as the mix layer begins to deepen again. So this is like a re-emergence theory that Mike Alexander talked about a long time ago, but at interannual time scale. So in 1 year you leave a deeper mix layer and a heat content to deeper depths, and then next year the mix layer shallows and leaves the warmer anomalies, which can then get entrained in a different season or a different year and so on, based on various processes. Okay, obviously you have to also worry about compound and cascading events. Compound events are generally defined as a combination of extreme conditions and or hazards that contribute to societal or environmental risk. As such, they stress both natural and human systems, causing socioeconomic impacts such as loss of essential ecosystem services and income. Understanding their underlying physical processes is thus critical for predictability assessments. So they discuss situations where multiple extreme events in the ocean can combine, or heat wave from the land, or a drought from the land and associated heating, etc., can combine with, let's say, coastal marine heat wave, and so on and so forth. But obviously the possibilities are there. Predicting and actually seeing when they happen and so on are always the challenge, right? So during a compound event, extreme conditions can occur simultaneously. So high ocean temperature and low oxygen concentration in the oceans can cause serious marine ecosystem losses, or in close sequence they can occur as well, where one event can increase the system vulnerability to successive events. So if you just had a heat wave event and then a cold oxygen deficit water intrudes, or some other deoxygenation process happens, then you have a vulnerable fish population just sitting there and getting choked when the oxygen poor water arrives. Okay, so droughts and heat waves can lead to higher risk of flash floods over land. Events can also occur concurrently over different regions with large scale consequences, as exemplified by the widespread impacts on fisheries caused by MHWs and low upper ocean nutrient levels during El Nino events. So in the Eastern Pacific, these tend to play out. So here are some examples of chlorophyll anomalies during marine heat waves. So this is a typical suppression of the upwelling in the Eastern Pacific during El Nino. So you have very warm waters arriving from the west, or reduced upwelling. There's obviously positive feedback, and you have suppression of upwelling and nutrient supply. Everything is reduced, and here again these are loss percentile chlorophyll anomalies, and you can see that there is also increases during certain periods. So this is just examples showing these heat wave anomalies during so H plus is basically compound events, so near surface biogeochemical anomalies and compound conditions during some impactful MHWs. Biogeochemical quantities are shown for the month and the area of the MHWs displayed on top, in the top panel of box 1's figure. Yeah, so we have to go back to the figure that we looked at before, this figure. So I won't go, you have to map yourself and so on. So let's just see what they mean by H plus. So percentile associated with the mean H plus anomaly during MHWs compared to the local empirical distribution of H plus monthly anomalies from 1982 to 2019 based on the observation data. So heat content anomalies, I suspect. Extent of MHWs co-occurring with low chlorophyll extreme event. So if you have low chlorophylls and then you have extreme event, the entire fisheries can get seriously affected. Okay, co-occurrent extremes during marine heat waves. So this is marine heat wave and low chlorophyll, marine heat wave and oxygen poor water, and marine heat wave and oxygen loss, as well as low chlorophyll water. Okay, so you can think of these hypoxic waters and so on and so forth. I'm being a little bit lazy, but you can go and read. How well do the models do? You can see the MHWs over 1950 to 2020 composite intensities. This is the ensemble average. This is from observations, and you can see models have plenty of biases, which are some of which are well known. And this is the maximum and minimum in the ensemble, and ensemble max minus min. Obviously models tend to exaggerate the El Nino impact, and models tend to have El Ninos that are too frequent, too narrow in the meridional sense, too far west, and so on. So those tend to feed into everything else that you look at. But you can also look at durations from the ensemble average and from observations for the 1950 to 2020 period, and you see the difference here: ensemble max, ensemble min, and ensemble max minus min for the duration. This is for intensity and this is for duration. Again, heavy influence of El Nino in the models. If El Nino indeed can help with predictions of MHWs, then all the better, right? So prediction of marine heat waves and associated biogeochemical extremes. These are long discussions. I'm just taking pieces. Understanding MHW predictability and building effective prediction systems can greatly benefit marine management. For example, accurate seasonal predictions of MHWs have the capacity to transform resource management practices that affect ecosystem services such as fisheries, aquaculture, and tourism. Motivated by many potential benefits, recent research has quantified sub-seasonal to seasonal MHW predictability and forecast skill using dynamical and statistical approaches. And they go through some details that I'm going to skip. So what will happen in the future? The ocean has stored more than 90% of the excess heat that has accumulated in the Earth system due to human-induced increases in radiative forcing agents, resulting in ocean warming that is projected by climate models to become large and widespread by the end of the century. Such slow background warming exacerbates naturally occurring temperature excursions, resulting in increased frequency, intensity, and duration of extreme SST events. Indeed, attribution studies have shown that the majority of the most impactful MHWs worldwide over recent decades could not have occurred without the influence of global warming. In the presence of the global warming trend, climate models project large increases in frequency, intensity, duration, and spatial extent of warm temperature extremes, and the magnitude of the increase becoming progressively larger at a higher warming levels. As usual, I give a caveat that the uncertainties in these can be high. Even on land, we struggle with producing very local information on heat waves, and broad scale heat wave warnings can be ineffective just in terms of how to allocate resources, how to get everybody ready, and so on and so forth. Some no regret decisions like setting up heat wave shelters, hydration centers, hospitals can be easy, but sometimes they have to be moved quickly to the most extreme events, and that needs very high skillful hyper-local predictions. Now imagine the oceans. That's going to be even trickier, and even if you can predict, then what do you do with it? This is very tricky, right? If you have a seasonal forecast that is reliable, then obviously fisheries management can take that into account, or tourism around coral reefs can be regulated, and so on. So here are the forecasts for March 98, November 2023, and these are the observations. As before, we have some skill, and a lot of times it may be based on El Nino. So the 97-98 El Nino was just about to die in April, May. It died away and led to a very strong La Nina, and so on. And then there is a La Nina here. There are parts of the ocean which warm up, which can be looked at. And in terms of, that's for the prediction part. In terms of the warmer climate, this is the mean SST change for 2070 to 2100 minus 1970 to 2000. As again, always I remind people, during these time scales, the uncertainties in projections largely come from scenarios. You know, we assume all those SSP 1 through 5 shared socioeconomic pathways, and they have all kinds of storylines which are considered useful for something or the other, but the uncertainties can be very high in that. Okay, so you can see which scenario that is. This is SSP 370. So there you go. MHW intensity change for this is the mean SST change. So you see warming everywhere except this cooling hole persists. MHW intensity change for the same period, you can see here is this is 2.54 degree average. This is 86% increase, but there are spots here. So you can look at regions: Arctic, Western Tropical Pacific here, Arctic, Western Tropical Pacific, and Northeast Atlantic. So there are shifts in the mean and the tails, and the news is not good if you believe the projections out to that scale. Let's just quickly read off summary and future perspectives. MHWs are an active and fast evolving area of research, and significant progress has been made in the last few years. Definitions of MHWs have been critically re-evaluated to best characterize these events and their drivers in the presence of the climate change trend, and approaches have been developed that incorporate spatial dimensions and time evolution. On the observational side, multi-platform systems capable of providing the three-dimensional structure of MHWs in the near real time are now emerging. Additional advances include a deepened understanding of local and remote drivers of MHWs, explorations of subsurface MHWs and their possible structures, investigations of land, ocean, and physical biogeochemical compound events, future projections of MHWs, and related uncertainty and evolving efforts in MHW predictions. Yet, to achieve a more robust assessment of MHW predictability, additional investigations are needed to better understand large-scale drivers of MHWs in different regions and during different seasons, and their interplay in altering local processes responsible for MHW growth, evolution, and persistence. MHW definitions should also be extended to reflect MHW mechanisms and allow event characterization based on their primary drivers. So we are still talking about fine-tuning the definitions themselves for MHWs. While many studies have discussed MHW impacts, this area of research is still evolving. For example, some long-lasting MHW impacts are just emerging, like the decline of the humpback whales in the North Pacific since 2014, attributed to loss of prey after the 2014-16 MHW. Conversely, other research suggests that MHWs are not a dominant driver of change in demersal fishes over the recent decades. I have a podcast on that, so we have to be careful about attributions. Aspects in need of further research include influence of MHWs on local atmospheric extremes like atmospheric rivers and heat waves, connections between temperature extremes and oceanic biogeochemical extremes, and long-term and cumulative consequences of MHWs on marine life across trophic levels, as well as assessment of recovery times in different regions. Also, given the reported impact of MHWs on air-sea CO2 fluxes and their documented association with cloud feedback in some regions, a deeper exploration of possible MHW influence on Earth's carbon and radiation budgets may be important. Finally, observations of physical, biogeochemical, and ecological quantities at the surface and especially in the ocean subsurface are key to all of the above aspects of MHW research. So there are many platforms already that show promise. Satellites, of course, deep Argo and moorings, and these many have been established for El Nino prediction and in all the tropical oceans and so on. Ships are involved. Now you have more and more gliders and so on and so forth. On the other hand, the systems that can be rapidly deployed for real-time monitoring provide not only a comprehensive characterization of individual events for prediction efforts, but also immediate guidance to decision makers. Such multi-platform systems, however, may not be feasible everywhere. Assessing which observations can most effectively monitor MHWs in different regions is a critical issue that the MHW community must address. Enhanced understanding of MHWs and their impacts is essential to guide and support adaptation and mitigation strategies. The tremendous level of ecological, economical, and societal losses resulting from these ocean extremes call for urgent actions to drastically reduce greenhouse gas emissions in order to limit the devastating consequences of climate change, which is true anyway, but obviously this will evolve similar to other science we do in terms of predictions and hoping that they will be used, and that is to see who can use them, right? So while I'm talking about users and engaging them, we have to essentially I was a bit lazy about H plus, so here we are talking about percentile associated with the mean, so H plus anomaly that I skipped in one of the figures, and the compared to local empirical distribution of H plus. So H plus is basically the percentile of the heat content, if you will. Okay, so let's stop it here. I don't know how long the podcast is, but it's okay. It's 38 minutes, a little too long. I used to split these things into multiple podcasts before, but now I'm just saying I'll do a long one, and you can listen to it at your leisure, and you can listen to it in pieces if you wish. But anyway, see you in the next topic.